That was the number one idea. Number two idea is the layered architecture behind the internet. What's a layering? It's basically a special case of something we see all the time. Okay, you can call the law of Lego. It's about modularization, okay, of a complex engineered system. You don't want to solve or design an entire complex engineered system like the internet with one shot. You would like to modularize the design and the control. As we said, that a protocol refers to a sequence of communication and computation to control the system. So a modularized protocol is what people call the layered protocol stack in the internet. You soon see this is not for efficiency. If you want to maximize efficiency, then you shouldn't use protocol stack layered. You should just integrate all the layers together and design specific protocol for each application. But it is designed, this layering, for evolvability, both in the business sense, because this allows specialization of business sectors and a common interface among them, but also for technology reasons. We have so many unforeseen and unforeseeable needs in the future for our technology that we'll rather keep an easy Lego stack where you can pull out one part of the whole system without having to redesign the entire system. And this is the most standard picture for what's called a reference protocol stack. It's called a stack because I don't know who started this, drawing pictures in a vertical stack of modules. Each block in the stack is a functional module. And because of this way of drawing things, we also call this a vertical decomposition, decomposing the overall functionalities of the network you desire into vertical blocks. Okay. And there are many such stacks. In fact, for each standard out there, they have at least one, often multiple such stacks. This is really a conceptual generalization. Okay, if you go actually look at Wi-Fi, which is only talking about the details of these two stacks, or you look at say 3GPP for cellular, they all have their own specific stacks. This is a conceptual picture, and this conceptual picture says there are 5 blocks. Okay, physical layer, link layer, network layer, transport layer, and application layer. Okay, so you must wonder what do these two things do, and what is this line here, this boundary between two protocol layers, and also why did I draw this thinner than the others? Okay, so 3 questions. 1, what does each block do? Each block does what? 2, the notion of this boundary between blocks. And 3, why is there so-called thin waist? Okay, because it's sort of like the waist part of a human being or something. Well, let's answer this one first. This is easy to answer. We draw this theme because there are not that many alternatives in transport layer protocols and network protocols. Pretty much the dominant ones are the TCP and the UDP protocols in the transport layer, and IP in the network protocol, in the network layer. Okay. In contrast, in the physical layer, we went from a copper wire, okay, to DSL or to fiber, wireless, and the wireless can be satellite, can be fixed wireless, could be Wi-Fi, could be 3G, 2G, 4G, LTE. This could be coax cable. It can be any kind of physical layer. The link layer also can be what's called ATM, it can be Ethernet, it can be Wi-Fi, and many link layer protocol. The application layer, we know this best. There are so many different applications. It started out back in the 70s for basically nerds and geeks with command line interface on a computer terminal in the 70s so that you can download some big files about some physics experiment, to, of course, emails, web browsers, to Facebook, to Twitter, to Netflix, to all kinds of wonderful applications that you're using today. So while the physical link layer and application layer changed so much, okay, 6 orders of magnitude, okay, that's 100,000 times at least increase in the physical layer speed, and such a dramatic enrichment of the applications, and yet the transport network protocol pretty much stayed the same across the last 40 years, TCP or UDP over IP. That's why we call it thin waist. It's sort of the visualization of an anchor point in the evolvability of the internet. Okay. Now let's go back to questions 1 and 2. What does each block do, and what is the meaning of this boundary? Each block provides basically the following kind of functional support. Each layer, each block, provides a service to the layer above it, and in turn uses a service from the layer below it. For example, layer 4 transport layer in the reference model provides an end-to-end connection. So it's responsible for things such as session establishment, packet reordering, congestion control, which we will see a lot in the next lecture 14 on congestion control. Now, it uses connectivity service offered by the network layer below it, and then it provides these end-to-end connection management as a service to the application layer above it to support things such as the web and email. Okay. So transport layer provides the end-to-end connection management, network layer provides the connectivity, link layer provides the access to the communication medium, and the physical layer provides the actual coding modulation to map the information to physically transmittable signals. Of course, the application layer runs all kinds of wonderful things that we directly interface with the internet. Now, what about those boundaries? There are actually a lot of functional overlap. That's why layering hurts efficiency, because you allow overlap. But it's precisely because of the need for evolvability that you have to encourage some level of overlap. For example, we all know there's a functionality called error control, right? You don't want the message to have a lot of errors. So who should be responsible for that? Okay. It turns out that everybody is responsible for that. The physical layer can do error correction coding, error correction codes. Okay, so add redundancy to the actual signal so that the channel distortion of the signals might still be recoverable at the receiver end. Now, link layer controls things like hop by hop retransmission. If you think that you didn't get it, well, ask the sender to send it again immediately over one hop. A network layer can do multipath and say that, well, if this path is corrupted, maybe signal along a different path can get it right. Now, transport layer can do end-to-end, not over one hop, but over all the hops end-to-end checking of the errors. Application layer can do, say, video coding that can ensure the robustness of the received video frames. So everybody is responsible for it. Okay. Similarly, if you look at the functionality of congestion management, well, you can change the transmission rate of the physical layer. You can run a different random access in the link layer. You can route it through a different path, avoid a congestion spot. You can do congestion control in the transport layer, or you can just adjust your video codec in response to the congestion condition in the network. So each functionality often can be manifested in many, sometimes all 5 layers. It's like the job of a CEO. Okay? Imagine you are the CEO of a big corporation, a huge one. Okay? So your job is not to sell a particular product or finish a piece of code. Your job is to do functionality allocation. Not resource allocation, but functionality allocation. The question of functionality allocation is who does what? At what time scale, and how to glue them back together. These are the 5 departments, for example, and your job is to coordinate their functionalities. Okay. That is the question of network architecture. Architecture is a heavily loaded, fuzzy word, but we're going to use it to denote this functionality allocation. And now we see that each line in this thin waist protocol stack picture represents a limitation. A limitation of what? Of what a functionality module can see, what you can observe directly, and what it can control. What are the degrees of freedom under your control? In the advanced material part of next lecture, we'll come back to talk a little bit more about viewpoints on how to design divide and conquer and how to design gluing back them together. For now, I'll just highlight particular interaction, the functionality allocation between 2 layers, 3 and 4. As we have seen, they collectively constitute the thin waist of this so-called hourglass model of the protocol stack. And there's actually interesting historical evolution in the functionality allocation and features between TCP, the dominant, one of the dominant layer 4 protocol, and IP, the dominant layer 3 protocol. For example, it turns out that TCP, as we will see in more detail next lecture, is connection-oriented, whereas IP is connection-less. What does this mean? Roughly speaking, it says that connection-oriented means you have to actually know that there is an end-to-end connection before you start talking. Okay? This might not be using dedicated resources because packet switching doesn't like that, but still you need to know that, hey, I actually have this connection before I start talking. This introduces protocol overhead that lowers your actual application speed, as we'll see in lecture 19. Connectionless basically says I don't even care if there is an end-to-end connection. I'm going to start managing the transmission hop by hop already. So here's an analogy. Phone calls is connection oriented. Okay, Alice calls Bob, and it rings, and then Bob picks it up, and then Alice starts talking. Normal human beings won't start talking even when the ringing hasn't stopped and nobody has picked up yet. But mail is connectionless. Right? When you send something, you don't first call them up and say, "Are you sure you still live there? Can you actually get my mail? Then I'm going to mail you something." Right? You just send it, put it in the mailbox. That's one difference. Why such a difference? Is that the only choice? Actually, not quite. Okay, people have discussed a connectionless TCP and connection-oriented IP. But eventually, people decided that because of the so-called end-to-end principle, they're going to let TCP or layer 4 be connection-oriented, layer 3 be connectionless. What is end-to-end principle? There's a famous paper on this in the early 80s, and it has caused also some confusion in different parts of the community as to what exactly does that entail. So one interpretation says that it says the network is dumb, the end devices are intelligent. Another interpretation, which is a little milder than that, says basically whatever functionality is best handled by the edge, by the end user devices, Google server and your laptop, then they should handle that. Right. So that still leaves the question open. How do you quantify that this job is best handled by end host rather than the network? Well, people believe that connection orientation should be handled by the end host. Another key difference between layers 2, 4, and 3 is load sensitivity. Okay, when a link gets congested, a lot of demand, not enough supply, we'll see more next lecture. What should we do about it? One notion is let TCP be load sensitive. Okay, and say that if this link is heavily congested, you should tell whoever is using this link somewhere out there on the edge, don't talk so fast. Okay, reduce your transmission speed. IP should be load insensitive. In other words, I shouldn't just switch my path selection. Say, once this path gets congested, then don't use it. Pick a different path in real time. Okay, the time scale of routing adaptation should be slower. The time scale of source rate adaptation can be fast. And since routing is done layer 3 it is load insensitive, and since source rate is controlled by layer 4, at least in TCP version of layer 4 protocol, then it should be load sensitive. Again, is that the only option? Not quite. Actually, people have looked at load sensitive routing and load insensitive end-to-end control, but decided not to do that. Okay, so each layer actually introduces overhead. At the top layer, your information is chopped up into units called messages, and then at the transport layer, chopped up into segments, and then each segment chopped into packets in the IP protocol, and then it chopped up into frames in the link layer. So as we go from layers 5, 4, 3, 2 down, we chop them up and then chop them up further, and so on. Okay. Each time we chop up, we actually add a little header in front of it. A little header. What does this little header do? It does a lot of useful things. For example, for the header at the network layer, it will tell you what are the addresses of the source and the destinations. But these also introduce overheads, as you can see. Now, as some information traverses from your iPhone to the server somewhere out there, web server or Google's video server for YouTube, you actually go through, of course, many hops, as we will see very soon. At different locations along the path, okay, along these hops, different network elements, for example, a switch near your home, a router in the middle of the internet, will process up to a certain layer. For example, your phone talking to a switch, let's say your residential gateway, may only use Wi-Fi and therefore only use the bottom two layers, layers 1 and 2, link and physical layer communication. But once it gets to routing layer, it has to also open up the network layer processing, because part of the job is decide what next hop you're going to route the packet to. Okay, and of course, once it gets to the server, it has to open up the application layer, because that's how you can start playing back the video. So the horizontal distribution of the hops also carries an implication to what part of the vertical layers do you process up to. Alright, so we have covered so far the key ideas 1 and 2 behind the internet: packet switching, layer protocol stack. The next thing will be distributed hierarchy.